Isomers are molecules that have the same molecular formula, but different structures. The word isomer comes from the Greek isos, meaning equal, and meros, meaning part. For example, these bromopropanes both have molecular formula C3H7Br, but the bromine is attached at a different position in each molecule. Or these two alkenes, they're both C3H5Br, but the bromines here hold different positions in space. It turns out there are several different ways for molecules to be isomeric. Constitutional isomers have different makeup or constitution. The atoms are connected together differently within each molecule. This is the case for the bromopropane isomers we saw a minute ago. In the left-hand structure, bromine is attached to the first carbon in the chain. In the right-hand molecule, bromine is connected to C2. Or these four molecules, all of which have the molecular formula C3H6O, but quite different bonding and connectivity of atoms in each case. There are different functional groups present in each of these structures, and the molecules are clearly very different. In stereoisomers, on the other hand, the atoms are connected in the same sequence, like the alkenes we saw earlier, CH3 to CH to CH to Br, but they still have different shapes, or different arrangements of atoms in space, to use the technical jargon. There are a few different ways in which this can come about. These double bond isomers are one example, where the rigidity of the carbon-carbon double bond locks the bromines into different positions. Or these two cyclic molecules. The two bromines can be on the same face of the molecule, both coming out towards us, indicated by the wedged bonds in the left-hand structure, or on opposite faces, one coming out towards us, one going back away from us, as in the right-hand structure. And even these two structures of the alkane-pentane have a different arrangement of atoms in space. The methyl group at the right-hand end of the molecule is in a different orientation. It turns out we haven't finished with new nomenclature yet. We need to distinguish between stereoisomers that can be interconverted by rotation about single bonds, these are called conformational isomers, and stereoisomers that can't be interconverted by a simple bond rotation, these are called configurational isomers. So looking back to the examples we've just considered, this pentane isomer, via rotation around the end carbon-carbon bond, easily interconverts to the second isomer shown on the right. These are conformational isomers of pentane, interconverting rapidly and reversibly at room temperature. In contrast, the two alkene isomers we looked at a few minutes ago can't be interconverted by simple bond rotation. That carbon-carbon double bond locks these bromines into position relative to each other, and these are configurational stereoisomers. Interconversion between configurational stereoisomers does not occur readily at room temperature. It's because the interconversion requires the bond to break and reform.